Hi, my name is Sarah Freeman, and today I'm doing a presentation on the study of wormholes for my elementary astronomy class. Wormholes are very much a mystery to the science community as well as astronomy, as wormholes are still considered a theory and not real in the sense, but we're able to gather some information and models on them, and I will discuss about that further in the slides below on such topics such as the theory of wormholes, the difference between wormholes and black holes, how they work, the different types they are, and the stability of them. The theory of wormholes. So the way we know about wormholes usually is through some type of sci-fi pop culture or media, such as like Star Trek, Interstellar, Doctor Who. And we very much fantasize about wormholes as some type of portal into another dimension or universe, but it's still considered a theoretical possibility and was first theorized in 1916, but they weren't called wormholes yet. They were still labeled as a subtype of black hole, but a solution was found in 1935 by Albert Einstein and Nathan Rosen, and the solution was a mathematical equation about black holes, and that solution was expanding past a black hole into the opposite area, which were white holes. And white holes are the opposite of a black hole. Nothing can enter its event horizon, as any material that goes into the entrance of it gets forcefully pushed out. Another aspect about the solution was aspect pairing, or hole pairing as Einstein and Rosen called it, is the idea of when two black holes collide with one another, they form into a single point of singularity. But the theory was what would happen if a black hole and white hole were to collide with one another. They would form a wormhole. Many people mix wormholes and black holes together, as wormhole is considered two black holes, but they're very different. Wormholes have two open points. They have an entrance and an exit, while black holes only have one entrance of singularity, single point of singularity, versus wormholes event horizons. You cannot enter it. You're forcefully pushed through the tunnel, while black holes event horizon, you can enter it but never exit it. The relativity physics for wormholes is quantum physics, while black holes is astrophysics. Wormholes also depend on negative energy and negative mass, while black holes depend on high mass and high energy. The other big aspect about wormholes is that they are theoretical and not observable. Black holes, on the other hand, we have actual factual evidence and pictures of them. Now that we know the difference between black holes and wormholes, we can now know how they function. So first you have number one, your accretion disk, and that is when any material or matter gets swept up within range and enters the rotating black hole, which you see at number two. And number two is a black hole that forms as a ring rather than a single point of singularity as a traditional black hole would have. And the gravity of this rotating black hole allows, quote unquote, for the singularity to sink in order to connect with the white hole on the other side. Then you have number three, which are your quantum effects. And this exists in this curved space-time, and this is what also allows for the tunnel to be open, which is negative energy or exotic dark matter. And without quantum effects, the tunnel will not be able to connect with one another, and it forces the singularity of a black hole to forcefully connect to the other side. And curved space-time, which is at number four here, is what all wormholes depend on. In our dimension, the third dimension, it seems flat on top, which is the side that the ship is on. But in the fifth dimension is when it curves on itself. This is where time folds and gives that theory of a shortcut through time. And then number five, you have your forced exit. Since nothing can enter the event horizon within a wormhole, it must come out the other side. Now that we know the basic functions of how a wormhole works, there are two different subtypes of wormholes, which is the Lorentzian wormhole, which is the one we just talked about, which is just a basic tunnel you go through, versus the Euclidean wormhole, which is the most fantasized type of wormhole, which is essentially like a portal where you just go in and out. There is no tunnel. Even though we have a bunch of models and information on wormholes, our main concern is the stability of them. They are very much dangerously unstable due to the consistency of two black holes colliding into one infinite density of a black hole and a white hole. There is a way to overcome this, though, is that the event horizon would have to be outside of the wormhole so nothing crosses the event horizon. But even if we were able to overcome this to have stability, there's still many different factors that we have to take into account, which is like requirement energy. Is there enough negative energy for the tunnel to not collapse on itself? Is there no interruption of the momentum of the object going through? Nothing hits it, as well as the object being able to withstand the radiation and gravitational force upon entrance and exit. And as much as I was able to gather this information for wormholes, there's still so much information that we do not know about yet. And hopefully in the future there will be more discoveries besides theories on them. I hope that this presentation was informational and enjoyable to you, and I thank you for listening. Hope you have a good day, and goodbye. Citations as well for the information provided.